Today we're going to talk about graphing square root functions. So let's begin by looking at the parent function, just f of x equals the square root of x. So it kind of looks like a sideways parabola, but only one half of it. Since we only going to have the positive part here, we can't really have the underneath part, this negative part, because if we did, then it would no longer be a function. It wouldn't pass the vertical line test. So we only have just kind of that one half of it, and it's that sideways U shape rather than having like a regular one like x squared. So the parent function has the following points. It's got 0, 0 on it. It's got 1, 1, 4, 2, and then 9, 3. And that's because if I take the square root of 0, I get 0. If I take the square root of 1, I get 1. If I take the square root of 4, I'll get 2. And the square root of 9 is 3. And then I make a smooth curve all the way through these points. And continuing on. Now the standard form of a square root function is the following. G of x equals a times the square root of b times the quantity x minus h, and then on the outside here, plus k. We have seen things like this, before in other functions, and it kind of works the same. So a represents our vertical stretch or compression. If a is larger than 1, then there's a vertical stretch of that amount. If a is less than 1, or rather I should say, if it's between 0 and 1, there's a vertical compression of that amount. And if it's negative, then there's a reflection about the x-axis. Okay, b represents our horizontal stretch or compression. This is kind of the opposite of what I would normally think. Normally, I would think if b is greater than 1 that there's a horizontal stretch, but really there's going to be a horizontal compression. It's going to squeeze inward of 1 over b. And the opposite here, if it's less than 1, so really between 0 and 1, I would think that there's a horizontal shrinking or compression there, but it's actually going to stretch 1 over b. And then, if b is negative, there's going to be a reflection about the y-axis. So it's going to flip over left and right rather than up and down. For h represents a horizontal translation or shift. So this is taking the entire graph and moving it left and right. And again, because it's on the inside here, it's working on x, I would think that if h reads plus h here, if it reads plus h, I would shift right that many units, but I actually shift left that many. And if it reads minus h, then I actually shift to the right that many units. So remember from previous functions that we talked about from standard form and how as we change these different parameters, horizontal changes are the opposite of what I would normally kind of think would happen, whereas vertical changes, a and k, the things on the outside of the square root, happen as I would intuitively imagine them to be. So as a gets larger, it becomes bigger. There's a vertical stretch. As it gets smaller, there's a compression. And then same for k. As it gets bigger, it goes up. And then as k becomes negative, it goes down. That is how I would think the graph would work. But the horizontal changes are the opposite. So let's talk about some examples here. So I've got, for number 1, g of x equals the square root of x minus 2. What I want to do is describe the transformations that are happening on this function in comparison to the parent function, f of x equals the square root of x. So I'm going to look for the differences. The differences between number 1, g of x equals the square root of x minus 2, and the parent function is that I've got, well, minus 2 on the x. And remember, the stuff on the inside happens the opposite of what I would think. So normally, if I go, oh, x minus 2, I would think go left 2. But the transformation that's happening here is I'm going to shift to the right 2. Whereas number 2, the square root of x, and then on the outside, plus 6. This is going to be a vertical translation. Anything that's vertical happens the way I would think. So this is going to shift up 6. Okay, number 3. This is another vertical change because it's happening on the outside of the square root. Here I've got 4 times the square root. This is going to give me a vertical stretch of 4. However, number 4, let's compare. This is now on the inside. I've got 8 times x on the inside of the square root. This is going to give me a horizontal compression, not a stretch, of 1/8. And then starting with number 5, we're going to mix and match. We've got 2 things happening. We've got a 6 on the outside, so 6 times the square root, and then x minus 7. So let's start with the 6. This is going to be a vertical stretch of 6. And then x minus 7. When I see minus 7, remember, opposite, because it's a horizontal change. So I'm actually going to go to the right 7. Number 6, I've got the square root of 1/5 times x. So again, this is going to be the opposite of what I think. Instead of being a horizontal compression of 1/5, this is going to be a horizontal stretch of 1 over this 1/5, or in other words, just 5. And then this minus 4 on the outside, this is a vertical change. We're going to shift. These things happen as I normally think, so this is going to be a shift down of 4. Okay, last one. The square root of 3 times the quantity x plus 9, so that's all on the inside here. These are both going to be horizontal changes, and then a minus 2 at the very end. So we're going to have 3 things occurring here. We're going to have a horizontal, not stretch, but compression of 1/3. We're going to be moving to the left, because plus 9, so shift left 9. And then finally, this vertical change, this vertical translation that's happening on the outside, that's going to be shifting down 2. So vertical changes happen as I think they would. Those are a little more intuitive. Whereas the horizontal ones, remember, it's kind of the opposite of what you would think should happen. Another thing we can do is find the domain and range of these square root functions. So let's say I'm given a function like this. G of x equals the square root of negative 1/2 x minus 2 plus 1. What I want to do is find the domain and range of this function, and then we're going to take a look at the graph of this. So here's how to do this. First, we're going to find the domain. To find the domain, we're going to set the radicand. That's the part underneath the square root. So this whole thing underneath the square root, we're going to set that greater than or equal to 0. So begin with negative 1/2 times the quantity, this is for domain, x minus 2 is greater than or equal to 0. And then we're going to solve for x. So what's happening to x? I've got negative 1/2 times this whole thing, and then I've got minus 2 here on the inside. So to get rid of negative 1/2, I can multiply by 2. If I multiply this by 2, And that'll get rid of my denominator here. I'll have negative 1 times x minus 2 is greater than or equal to 0 times 2 is, well, that's still 0. Okay, I can divide by this negative 1/2 now, or negative 1, I mean. So on the left, I'll still have x minus 2. 0 divided by anything is still going to be 0. But I've got a rule here. Anytime that I multiply or divide both sides here by a negative, in this case, I divided by this negative 1, I have to flip the sign. So this is no longer going to be greater than or equal to. Now this flips over to less than or equal to 0. And then I'm going to add 2. Okay, so x is less than or equal to positive 2. This is the domain. Okay, now let's look at the range. For the range, what I'm going to do is I'm going to set the entire radical here greater than or equal to 0. And then I'm going to kind of what I like to call build the function. So what do I mean by that? Start by writing down the entire radical and everything inside of it. So let's say this is the square root of negative 1/2 x minus 2 here. Okay, and this is going to be set greater than or equal to 0. Then what I do is I compare what I've got written here to my function, and I go, what's missing? Well, what's missing from this is just this plus 1 at the end. So that tells me on the left side, I need to put this plus 1 in. That means that I'm going to do that to the right side as well. So I'm building the function up to what it actually reads. Okay, so then this will give me the square root of negative 1/2 x minus 2 plus 1 is greater than or equal to 0 plus 1 is 1. Well, this is now what this function is. And this function is g of x, which this is just fancy for saying y. Y is greater than or equal to 1. So this is my range. And then what I would do here is I would make a graph. So I'd make some coordinates, and then I would plot some points here. So I would test some points x and y. You could also start with your domain x is less than or equal to 2, and your range is greater than or equal to 1, and that'll help determine what your initial point here is going to be. What I've done is I've just gone ahead and graphed this in Desmos to show you what this graph is going to look like. So normally this goes to the right, but because we flip this sign, x is less than or equal to 2, we're going to begin at 2, 1. Does that sound familiar? X is less than or equal to 2. Range is y is greater than or equal to 1. So 2, 1 is our initial point here. And then instead of going to the right, we're going to go to the left because of this negative on the inside, reflecting horizontally. But let's say that I start with a graph and I want to find the function. That's another problem we could do. So writing the function of a square root function given its graph. Okay, well, the first thing I want to do before I do any of this, before I read any of this, is I want to remind you of what the standard form is. So let's write that down over here. The standard form is a times the square root of b times the quantity x minus h on the all on the inside there, and then plus k on the outside. So I've got two facts. My initial point is at hk. So h comes from the inside here, x minus h, and k is what's on the outside here. A second point is found at h plus 1 over b, k plus a. So this is my x value of my second point. This is my y value of my second point. And once I know what all of these h, k, b, and a are, then I can write this in standard form. So let's say I'm given this function, okay, this graph. What I want to do is first find my initial point. My initial point is where this graph kind of begins, if you will. This is an x value of 1 and a y value of -2. Okay, so let's write down my initial point. This is at hk. But my actual point here is 1, -2. Well, what does this tell me? If my initial point, kind of the formula about it, the fact about this, is at hk, but my actual point is 1, -2, then that means that h equals 1 and k equals -2. Okay, let's put a box around those, and we'll highlight those so we don't lose them later. All right, now let's talk about the second point. My second point, kind of my formula for it, or my fact about it that I said, is that it's always at h plus 1 over b, and then k plus a. Well, what is my actual second point here? This is 0, -1. So this tells me that I can break this up and I can say left equals left, right equals right. So h plus 1 over b is going to be equal to 0, left equals left. And over here I can say k plus a, this is going to be equal to -1. The right here equals the right here. Well, I happen to have found h and k already. H is 1, k is -2. So what I'm going to do over here is I'm going to say h is 1. So let's plug that in. 1 plus 1 over b equals 0. And then I know that k is -2. So over here I can say -2 plus a is equal to -1. All right, let's start with this left one. Solving for b, it looks like I'm going to subtract 1 from both sides. So I will get 1 over b is equal to -1, which -1 is just -1 over 1. You'll see why I'm writing this as a fraction in a moment. I'm solving for b. Currently, I've got 1 over b. So what I'm going to do is I'm going to divide by, I'm going to just basically, this is 1 over b. I'm going to take the reciprocal of the left side and just make it b over 1. Okay, 1 over b, flip that upside down, b over 1 is equal to -1 and then flip this upside down, it'll still be 1 over 1. Or in other words, I could just say b over 1 is b, equals, this is negative 1. Okay, let's highlight that again so we don't lose that. And then over here, I've plugged in for k. Looks like I'm going to solve for a. So I'm going to add 2 to both sides. And I'll get a is equal to negative 1 plus 2. That's positive 1. All right, now let's put it all together. Again, reminding you, the standard form is a times the square root of b, quantity, x minus h, that's all on the inside there, and then plus k on the outside. Okay, let's write that down again. This is going to be a square root, b, quantity, x minus h, and then plus k at the end. I now know a, b, h, and k from what I've found. Let's go ahead and fill it in. Let's say f of x or g of x. I don't think I was given a name, was it? No. So we'll just call it f. F of x equals, a is 1 times the square root, b is negative 1 times the quantity, x minus h, x minus 1. Then on the outside, plus k, so plus negative 2. I can just say that's minus 2. F of x equals 1 times the square root of negative 1 times the quantity, x minus 1, minus 2. From there, you could simplify a little bit, but I'm also okay with this. So today we've learned how to define what's going to happen in the graph of a square root function given its parameters. We've learned how to find the domain and range of one of these square root functions, as well as, given the graph, how to find the actual function for that graph in standard form.